Hello, my name is Omalde and this is Lab 5, Motion of a Tennis Ball Tournament. Introduction. The purpose of this lab. For this lab, I chose to study a motion of a tennis ball that is being thrown up in the air and then falls down and is caught. In this lab, I will be exploring Newton's second law with the non-constant force. I will also be exploring the impact of instantaneous force. For the sake of simplicity, I will be ignoring the force of drag. The models and fundamental physics principles that will be studied in this lab are the following. Firstly, forces on objects. Gravity will be studied, which will be constant, and the throwing force will be studied, which will be an instantaneous, therefore non-constant force. We will also be using the position velocity update formula, as well considering a non-constant velocity while falling. And a quick preview of the main result. The prediction model will match the observed results, as well as the calculated approximate force that was used to throw the tennis ball will be about 0.2 newtons. Here is the tracker analysis of my ball's motion. Here you can see the observed data in the middle with an equation trend line for it. There on the right, there's a screenshot of the tracker video used, as well as my initial conditions for this experiment were height 0 centimeters, time 0 seconds, a net force of 0.20 newtons, which was calculated, a velocity of 3.330 meters per second, a gravity of 9.8 meters per second square, and finally a mass of 60 grams, which was the Google search average tennis ball mass. Here is my computational model. In the top screenshot, you can see my initial conditions. This lists my initial mass of ball, my initial instantaneous net force, as well as my ball position and ball velocity, which is calculated using ball mass and initial net force. Then there is my time and my data time, which was calculated using the steps found in the tracker video. And finally, there is the gravity and drag constants. In this case, the drag constant is 0 as drag is being ignored. In the second screenshot, I am calculating ball's position and its velocity for every second. This uses the net force on the ball, which is calculated just using the force of gravity. And then that is used to step through the ball's velocity at every moment and therefore the ball's position at every moment. Time is also updated during every loop using the value for the delta t time step. Here, the predicted data from the computations is visualized. On the right, you can see the visualization used from CloseScript, which shows the position graph and the velocity graph. Position graph as a parabola, while the velocity graph is a linear decrease as there's constant force of gravity acting on it after the instantaneous force has already been acted on. On the left, there's a graph created using the predicted data calculator. This also has a trend line for the equation that you can see down below. Here, you can see the observed and the predicted data being compared to each other by being plotted on the same graph. Because the observed data includes the ball not being thrown for a couple of seconds, it is slightly shifted to the right compared to the predicted data. It can also be noticed that the predicted data is slightly narrower than the observed data. This is most likely due to the force of drag not being considered, which would slightly slow down the effect of gravity and hence would lead to a slightly slower time to reach back to the ground. However, despite these two differences, the trend for the data is mostly similar as both datasets follow a distinctly similar parabola. Discussion. So, what do these results mean? Well, based on our calculations, the initial force we applied on the tennis ball to make it fly the way it did was a force of 0.2 newtons. This was calculated through trial and error and can be seen in the accuracy of the predicted data to the observed data. Again, the observed motion mostly followed the predicted models. This shows that the Newton's laws of motion were mostly observed, with the exception of the force of drag as we discussed earlier. What are some possible errors in this calculation? Firstly, this computational model could have been a bit simplistic, aside from ignoring the force of drag. It also counted the force of the hand being thrown to be instantaneous with no time taken, while in reality it took a couple milliseconds for the force to be applied on the tennis ball before it accelerated to the initial velocity. Finally, there could have also been manual tracker error as the tracking on the application of tracker is not perfect. What are some what-if questions we can ask with this experiment? Firstly, what would happen if the tennis ball was replaced with a paper ball? Since paper ball would experience a lot more force of drag compared to a tennis ball, we would assume there would be a much bigger difference in the observed versus predicted data, and perhaps the force of drag would have to be considered with the predicted data to be even close to accurate. Secondly, what if the ball was thrown at an angle? The horizontal movement could lead to a slight change in the vertical displacement. Thank you.